when I talk about rail durability, and I want to talk about rail durability in sense of surface life durability. So what's the consequence of surface conditioning for the surface life of the rail? Before going to the subject, I want to make a very short excursion with you in the domain of rail materials. I think that most of you, this picture looks quite cryptical, but I'm going to explain it. I think the basis of this picture, most of you are very familiar with it. I just took it from an InnoTrack report, and this InnoTrack report compared the behavior of different rail grades in terms of wear, sensitivity to wear, and RCF, so the number of cycles needed for a sample to initiate rolling contact fatigue. So I think many of you are familiar with these two lines, these two curves, and this graph basically also is used as I would say, the basis of many regulations for national railways for the selection of grades to use in the track. Well, the first thing, when you compare these two graphs, is when you, I should first say something else. On the horizontal axis, you see here the rail hardness, and I limit the values from 200, in this case, to 450, and that's about the values that are achievable nowadays. So in old tracks, there are still some 200 grades, and we are talking, some companies are talking about this area, developing rails in this area. When you move now from, in a small bandwidth on the horizontal axis here, you see what happens. On this RCF axis, yeah, you increase a very little bit the RCF sensitivity. When you move of the same amount in the wear graph, you see that you spend, I would say, a much larger portion of the available wear window. And when you do this exercise for the two grades that are most used, the 260, that's this line, and the 350, you end up with these numbers. Of course, these numbers are just indications. Don't take them as exact values, but they are quite significant. If the entire window from 200 to 450, we assume that it is 100%, so this is the available wear window. We do the same for the RCF. So we have an RCF window from here to here. And you move from the 260 to 350, then you use 40% of the available RCF window and 94% of the available wear window. Well, again, it's not about numbers, but these values are completely different. It's a completely different order of magnitude. And I think we have here one of the reasons why, in practice, the concept of a magical wear rate, that remains purely theoretical. It's almost never achieved outside in track. So we can talk a lot about it, how nice it is and how nice it would be to have such a magic wear rate, but it cannot be achieved in practice. Of course, this has consequences outside in the field. When we look again at this graph, at the left we have a typical degradation regime, which is wear. So the softer the rail, the higher the wear. And at the right, we are moving into the RCF degradation regime. So here are some illustrations. This is the typical behavior at the left side in this chart, and this is typical behavior that we find at the right side. So what happens in this case? Here in this case, when this happens, we have to do some maintenance, because we have to bring back the original condition of the rail in some case, somehow. Here at the other side, we have to do exactly the same thing. We also have to do something in order to mitigate this. So what are we going to do here? At the left, we are going to do what is traditionally called rail reprofiling, and we have norms for that. The requirements are in this European norm, and I think many international norms or worldwide norms have the same type of norm, and it's a geometrical norm. It says that the roughness, it's mostly related to roughness. It's very typical. When you look here, also it's in the title of the norm, it talks about reprofiling. It's always about reprofiling. Now we are going to the right side in this chart. So what kind of maintenance do we apply here? And when you look from a historical point of view, basically what we have done is just copied this type of maintenance. We have copied over the entire graph, and we do the same thing at the right here. So basically we are also reprofiling here our rails, and we use the same requirements. And that brings me to the subject of my presentation. There is a relationship between the way that you maintain the rails and the life cycle of the rail. And I show this in this graph. This is the RCF life cycle, so we talk here only about RCF, not about wear, because we got the right side in the graph. And here you have the borne tonnage, and you see here the growth of the defects. And here somewhere are what we can call initial conditions. So when you are able to set back the initial conditions to 0, you again have this tonnage window. When you do this in a less appropriate way, you can shorten the life cycle. And in very bad cases, I think many of you are familiar also with what can happen then, you can get severe spalling. But there is a lot in between. There's a lot in between a case of, I would say, damaging the rail just by the treatment, or setting it back entirely to 0. And these initial conditions, that's the subject of my paper. One of the ways of looking at this, and in my view, a very efficient way of looking at this, and looking at any surface treatment method, is looking at the energy flux during the treatment process. So if you have here a worn rail, or a damaged rail, whatever, you need to make a certain input of energy per surface area in order to treat the surface. And basically, there are 3 dissipation mechanisms in this top layer which govern the surface conditions after treatment. And typically, these 3 mechanisms also lead to a stratification in the surface properties. So a treated surface always shows some kind of stratification. And the first layer, well, it's invisible because it's removal. So that's a large part of your energy input goes simply into removal of material. The second one is transformation. So energy is transformed into heat, and that leads to something in your material. Something happens. That's transformation. And the third one is below that layer. That is plastic deformation. So energy is used for plastic deformation of your material. And I think that you can capture with such a model, you can capture any surface treatment method. It can be grinding, milling, or whatever. And I think in order to have a proper process, you have to tune the distribution of the energy over these 3 processes. And I will go deeper in that. If you exclusively tune this one, removal, you can get a very bad surface, and you can reduce the lifetime of your surface with large factors, and also come back to that as well. Something which I want to show also is that the wheel-rail interface, and that's something this conference is about, it's a tribological pair. It's not 2 different worlds, but we're treated often as different worlds. If you look at the rail surface and at the wheel surface, well, there are a lot of differences. The most striking one, of course, is the extension of the surface. Here you talk about a length of 3 meters, roughly, and here you talk about thousands of kilometers. But still, a material point in the rail, for example, take this yellow point, it is not interested in the length of this rail. This material point just feels each time the wheel passing by. And it's not interested in what happens at other positions. So if we look at it as a tribological pair, we should compare the surface conditions at both sides. And also, for example, look at norms at both sides, the ways that the surface is being treated at both sides. Well, I didn't put here the norms, but if you look at these norms, well, they are completely different. It's like 2 different worlds. If you look to the treatment method, well, I think most of the wheels, all of us know, they are being reprofiled by turning. So you always have a milled surface here. And most of the cases you have a ground surface at the other side. So does that match somehow or does it not match? The differences, well, the spatial dimensions I talked about. Well, another striking difference with other tribological systems is that it is a non-confined system, so water can come in, a lot of other materials can come in. But there's also a big design difference. If you look to, for example, a roller bearing, it's always designed in such a way that the frictional work is minimized. There should be no frictional work in a roller bearing. But if you look to our railway system, even if you are at the very beginning of the traction curve, the adhesion curve, you always have, by definition, frictional work in wheel rail contact. And this has a big consequence for these surfaces. And that's also something we'll come back to. Which aspects are now important in tuning such a treatment process? Well, in view of the time, you see it, and I will not go into detail into each of these aspects, but I'll just list them. They are in the paper, so if you are interested in them, please go to the paper. There's the presence of a white etching layer. There is the discrete versus the continuous character of such a layer, the thickness of the layer, the internal uniformity of the properties of such a layer, the nature of the white etching layer and the constitutive properties in relation to the parent material, the degree of bonding between both, the presence of subsurface plasticity, the residual stress profile, and the surface geometry. And all of them are grade dependent. This I skip. I just want to take out one or two aspects to illustrate the difference. You see here in this graph, which is not by my own, but it is from the literature, you see for different processes, you see the residual stress profile in the subsurface. And I'm not going into detail, but if you look to milled surface, you get compression into a large part of the subsurface. When you go to grinding, there is the residual stress profile is like this. There's a lot of tension. And it has big consequences. If you look to the fatigue life for these four methods, and I'm again not going into too much detail, but the difference between milling in a proper way and grinding in, I would say, an aggressive way, well, the difference between both processes in terms of lifetime can be 1400%. And again, this is not about small values or exact values, but the order of magnitude is very significant. And that means that there is a lot to gain, I think, in this field. Well, this is a very interesting aspect, but we have only 1.5 minutes left. So I would like to end up. Yeah, that's true, yeah. So if you want, we can discuss this, because the discussion is just afterwards. Here you see for three different grades, the 370, the 350, and the 360, you see a ground surface, and there is roughness in all cases, but you can also see that there is white etching layer in all cases, and it's completely different. Here you have a small band at the outside of the running band. Here, yeah, this is a curve where you also have a specific band with white etching layer, and here it's over the entire running band. And in all cases, the white etching layer is clearly related to the running band and to the roughness. There's a relationship between roughness and white etching layer. When you look back to the history of these samples, well, in this case, for example, this is 350 and a high leg of a curve. Here, this seems to be related to an interaction of frictional work and roughness at the outside of the running band. So this is typically caused by spin. There's a lot of frictional work here at this side of the contact, and in combination with roughness, this leads to phase transformation of the higher portions. So what I would like to say with this picture is it's not sufficient to look only at roughness, to look only at geometry, but it is necessary to look also at other aspects. It should be an integrated approach.
Sorry for what you would like to say, but you are out of time.
Yes, I'm stopping.
You used quite a lot of time for the introduction of what
yes.
we are going to say. Sorry for that.
No problem.